Hello everyone, I am MD Rafiqul Islam Robin, a computer science PhD student from the University of Houston. I will present our paper, Syntax Guided Program Reduction for Understanding Neural Code Intelligence Models. Deep learning has increasingly been used for various code intelligence tasks. In those tasks, the model takes a program as input and makes some predictions about the underlying downstream task. For example, predicting method name or detecting bug. Although successful in modeling source code, the problem of explaining why models make their prediction is still challenging. This is because the deep neural models are opaque black box and offer little insight into the features they use in making their predictions. In this regards, we propose a model-agnostic approach to identify relevant input feature to a model's prediction. This is an example from the method name prediction dataset. A developer looking at this program could provide several explanations why this is onCreate method. For example, there is a super.onCreate invocation that strongly suggests that this method overrides a method with the same name in the parent class. Also, if developer familiar with Android activity, they can recognize that onCreate method is used to initialize a user interface with setContentView. A trained code intelligence model can correctly predict this code snippet as onCreate, but it is difficult to understand what feature actually such models use for making this prediction. To improve the transparency of models' prediction, we aim to extract input feature that models have learned during training. This is the high-level overview of our proposed approach for extracting key features from input programs. In our approach, we adopt program reduction algorithm to remove irrelevant parts from input programs and create candidate reduced programs. The approach then checks the predictions of the target code intelligence model on the candidate reduced programs and continues removing programs by preserving the model's actual prediction. Finally, we extract key features from the reduced programs. In our previous work, we used delta debugging as reduction algorithm to reduce the size of an input program. Given an input program P and a model M, the approach first records the target prediction Y given by the model M on program P. Then delta debugging produces a candidate program by removing some parts from the original input program. If the reduced program does not provide the same prediction Y, it then rejects this candidate. Next, it creates another candidate by removing some other parts from program. It then iteratively searches for the final reduced program R that produces the same prediction as the original input program. However, the delta debugging approach does not follow the grammar of the programming language during the reduction and create a large number of invalid programs, which hinders the overall performance of reduction. Therefore, in this work, we adopt Perses as reduction algorithm that follows the grammar of the programming language and always generate valid input programs, which improves the overall performance of the reduction. Given an input program P and a model M, the approach first records the target prediction Y given by the model M on program P. Perses then parses the input program into a parse tree by normalizing the definition of grammar. Then it traverses the tree node by node, and determines whether a tree node is deletable, depending on whether deleting it preserves the same prediction Y. It repeatedly checks each tree node and prunes the subtree when node is deletable. And after checking each tree node, the remaining program is the final reduced program when no further node can be deleted, that produces the same prediction as the original input program. We have applied our approach for the method name prediction task across two popular code intelligence models, Code2Vec and Code2Sec, on the Java large dataset, including different types of input programs. We first discuss our approach for automated feature engineering and demonstrate how it can be used for adversarial attack. Then we provide a comparative analysis between different program reduction approaches. In our previous handcrafted embedding org, we attempt to find key input features of a label by manually inspecting some input programs of that label and then train a SVM model. However, this manual inspection does not scale to large dataset with many labels. To automate the process of extracting key features that models have learned during training, we apply our prediction-preserving reduction approach. Given a trained model and a set of input programs of a target level, the approach reduces those programs using program reduction techniques. After reducing a set of input programs of a target level, we extract tokens from the reduced program. The most common tokens are identified as key features for that level. These are key features that came up with our feature extracting approach. There are many overlaps between the model's extracted features and the ground truth handcrafted features marked as blue color. Those can help developers to verify whether a model is learning a label correctly or debugging the cause of mispredictions. Also, by extracting key features for all labels, we are actually representing an abstract form of model's feature space. The learned feature space will become more transparent. In our previous generalizability org, we observed that models are very sensitive to variable names and often change their prediction on variable renaming transformation. For example, in this original program, there are 4 variables. If we rename any of this variable name, the model may mispredict the program. But which variable is more sensitive to adversarial attack? We can find such potential vulnerable variable by looking at the reduced program. The variables that are kept in reduced program are more likely to sway the prediction of original programs. While in our previous org, we create candidate adversarial examples considering all variables of original programs, in this org, we create candidate adversarial programs considering only key variables from reduced programs. We observe that in each scenario, the number of generated candidate examples based on key variables is almost 50% lesser, but on average, those can trigger more than 10% misprediction. Comparing delta debugging and Perses, the Perses generated candidate programs are more vulnerable to adversarial attack than delta debugging, with fewer candidates than delta debugging. This might be highlighting the importance of key tokens found in Perses generated reduced programs. Finally, we provide a comparison between delta debugging and Perses on the reduction performance. From our experiment with different input types, we observed that Perses allow more token removal than delta debugging, is more likely to reach the final minimal program in a smaller number of reduction steps, which decrease the total reduction time, especially for the larger size of input programs. Using different reduction techniques, we can find different potential explanations about a prediction. For example, a code intelligence model predicts the code snippet as the onCreate method. In delta debugging with token-based program reduction, we can see that set content view has an important role in the target prediction. On the other hand, tree-based Perses highlights the presence of the same override method in the program. Having this multiple explanation for a specific prediction may provide additional explanation for transparency. However, the challenge is how can we summarize those multiple cues from different approaches. In future, we plan to focus in this direction. In summary, we adopt Perses as a reduction algorithm for extracting key features that models have learned during training. Using the syntax information, Perses improves the performance of the overall reduction, as the reduction only explores the space of syntactically valid programs. By analyzing reduced program, we can explain the prediction of the models, and we can identify relevant input feature to a model's prediction, which may improve the overall transparency of a model's prediction. The adversarial evaluation with key identifier also highlight the importance of key tokens found in reduce programs. Thank you. We have made our artifact publicly available for further study.